Good morning, good afternoon, and good evening, everybody. Welcome to the talk. It's going to be a little different. I was trying to figure out how to actually do this talk, so it'll be a little different. My colleagues, I think, but hopefully enough for some conversation. Initially, what I did want to start off with, though, was just a recognition that yesterday in Canada we had a National Day of Truth and Reconciliation, which is a day that honored survivors, their families, communities, and commemorates their history and the legacy of residential schools as a part of reconciliation. It's an important activity and a new national holiday in Canada. And even though the conference is virtual, I do want to do a territorial acknowledgement at the University of Alberta. At the University of Alberta, we respectfully acknowledge that we are located on Treaty 6 territory, a traditional gathering place for diverse Indigenous peoples, including the Cree, Blackfoot, Métis, Nakota Sioux, Iroquois, Dene, Ojibwe, Saulteaux, Anishinaabe, Inuit, and many others whose histories, languages, and cultures continue to influence our vibrant community. So for the talk today, what I would like to do is just a really quick overview of the chair activities. There's just a couple slides, and then really it's about a conversation about a factor of safety. There's lots of conversations these days around that term, specifically around caprock integrity. And so just going to share some thoughts and see what people in the audience might think about it. Our chair program and NSERC Energy Simulation Industrial Research Chair Consortium is continuing to look through the full scales, all the way from pore scale all the way to field scale, through a series of experimental numerical field data approaches across a wide spectrum of materials. Oil sands, I think there's still a fair amount of work to be done in oil sands and shales and understanding how that very complex geology system works under thermal recovery systems, and then into tight oil and gas type activities as well. The other thing that we are looking at is something and launching something called Geosafety, which is a program really around subsurface assurance for energy technology. It crosses the full range. We're trying to leverage off our almost 20 years of experience in CCUS and really start looking at things like other aspects of subsurface use, massive scale up of CCUS, hydrogen storage, geothermal systems. These days, many people are trying to marry CCUS and geothermal. There are some complications with that. And then spending a fair amount of time recently with granitic and sedimentary sequences for nuclear waste disposal is bringing on some interesting challenges. And so that's something else that we're working on, and it's a separate issue, but it builds on and supports the work that the Energy Simulation Consortium is working on. So factor of safety. Lots of talk, lots of discussions, lots of work around really what a factor of safety really does mean. One of the things that you will see when you look at the definitions for a factor of safety, and you'll see this word many times, is it will talk about a system. So when you look at things like the buildings, pressure vessels, planes, components of planes, you will see that there are, this word is a system, and we tend not to many times use that as a word in caprock integrity, but and we'll chat about that in a minute. But one of the other things that you see is that in a building, you might have a factor of safety overall, factor of safety of 2, pressure vessels, might be as high as 3.5 to 4. And then something as critical as airplanes, you look at landing gears and they're down at 1.5. And that really has to do a lot with reliability, to be able to test components over and over and over and over again in order to demonstrate reliability. And so you can get away with lowers of factors of safety if you can build that kind of reliance and reliability into your testing. But if you can't, or if the risk is too high, pressure vessels, then the factors of safety go up. And we have that same conversation that we have to worry about in subsurface processes related to caprock integrity. So, lots of uncertainties. Most of the chairs, they're all very familiar with this, working in all different aspects of this. But, factors of safety by themselves include a whole range of stuff. There's a large empirical part in there, but it's meant to minimize damage, costs, change probabilities of failure by changing factors of safety, reliability in data, how something is constructed for subsurface, what the properties look like. Many people that are working in the chair program have a lot of those backgrounds. So, the motivation for this really was, how do you define failure for caprock integrity? So again, inability of a system. So if you look over at Jocelyn, the very famous event in 2006 changed the kind of way that we look at caprock integrity for thermal recovery. That was really not the failure of one little tiny element somewhere, but it was the failure of a system, a caprock system, to contain steam. And so if you looked at this, it was a non-performance of what was requested. We want the caprock to perform in a certain way. And so it really was about a system response. And so that's kind of what motivated our thinking a little bit about this. And I was intrigued actually at the words, so how many, if you go into something like Compendix or something else, and you search for caprock integrity, you can find lots of records. But if you look for caprock integrity and factor of safety, there's only 3 records and they're all related to SAGD. If you switch it around and say safety factor, there's 5 records, still all SAGD. Caprock integrity and CO2, and I make a point about factors of safety and CCUS, but more records. But if you look for caprock integrity, CO2, and safety factor or factor of safety, no records. I did find one. You've got to search really hard in the text. But of the papers since 2010, nobody's referred to a factor of safety. And other things. Induced seismic, we talk a lot about induced seismicity for a lot of things. So should we, in certain things like hydrogen storage, CO2 storage, should we be talking about a factor of safety against exceeding a particular induced seismic event? So, and there are ways to do that, but we don't typically use the word factor of safety. Factor of safety entered the language mostly because of the regular requirement, the issuing of Directive 86 in Alberta, since the Jocelyn event, and it actually states to compute the factor of safety. Margin of safety is sometimes used, but it wants to compute the factor of safety against tensile and shear failure. So that directive, in terms of maximum operating pressure, wants you to actually define a factor of safety against 2 primary mechanisms. One is a tensile failure and one is a shear failure. And then that's what you have to determine for your MOP. And so if you look at tensile failure in terms of Directive 86, you get an equation like this. I think I should probably pick that. So you get an equation where they've called this a safety factor. It's not quite a safety factor, but it's like a reduction factor of 0.8 times an estimate of this minimum stress, which is a fracture closure gradient calculation in the caprock, and a depth to the base of the caprock. And so essentially what you're getting is a sort of relationship between the injection pressure and this minimum stress that's determined inside the caprock. And what this comes down to essentially is a factor of safety of 1.25 is essentially what that comes to. So what you're trying to do is design your projects to a factor of safety against tensile failure modes of 1.25. What's less understood is shear failure. But the words in the application say that you should actually, as a part of this thing and define a factor of safety around shear failure, is the pressure at which shear failure of the caprock is predicted to occur. So this is the part where now in all of the modeling that we all do in our Energi simulation family and out of all of the programs, we're at a point where we need to predict failure. It's not just a process. We actually have to try and figure out what that failure mechanism was. And so in generally, a lot of times people will come in here and we'll do something around what's called a strength envelope, and they've got friction angles and cohesion and stress states, and we do some modeling and we do some stuff and we get some values. And so if you look at this, so then should I also be designing the shear failure to 1.25, which is the same as tensile? Which one's riskier? Which one do we have less knowledge on? Which one is more uncertain? And those are not insignificant questions to answer. The other question is should we be using something called probability of failure? And there's actually a better term, I think, quite frankly, is that in certain bits of the literature, is a probability of unsatisfactory performance. So there's a particular threshold, a set of characteristics that we want our system to behave to. And perhaps we should be saying a probability of unsatisfactory performance of our system as opposed to a probability of failure. Some work that's been done in geotechnical engineering, if you look at this upper right-hand curve, you see factors of safety. If we generally define a factor of safety of 1, we typically think we're at a point of incipient failure. And so in here you can see that this is about 0.6, probability of failure of 0.6 as a kind of a number. There are lots of things that we can do. Let's say if we get a variation, we have just geostatistical problems, realizations, we can generate a bunch of scenarios where we generate a distribution of factors of safety, and the area under the curve here represents a probability of failure. But we have multiple scenarios, multiple pathways. Some of the work we're trying to do in order to try and speed this up so that you can run realizations like that is a bunch of work on upscaling to try and allow us to do reservoir geomechanical simulations more quickly than are currently done. The other thing is pathways. I mean, these requirements ask us for description of potential pathways, failure mechanisms. Same is going to happen for, you can make the point the same should happen for CO2, hydrogen, salt caverns, geothermal. You do a risk assessment. This great work done by Gort Stab, I think it was at Suncor at the time, identifying particular pathways of escape. Well, each one of these would have a particular factor of safety. It's not a single factor of safety against 1.25. Each of these mechanisms defines separate factors of safety. CO2 injection, other subsurface use, geoenergy use, the other paths to the surface. All of these would represent separate calculations of factors of safety. So in terms of our simulations, how should we do it then? Everybody does simulations. We will see a lot. There's a lot of really outstanding simulation work done by the Energi simulation family. So we do a simulation, we have a caprock, it can be an oil sands reservoir, it might be CO2, something, whatever it might be in terms of your problem, and I pull out the caprock response. Well, should I worry about the whole caprock sequence? Should I worry about each separate element within my model and do something where I integrate them? Or should I only worry about just these elements down at the bottom here as a way to determine whether I am, at some point tensile or shear failure? So we can do some things. I can assume a failure mechanism, say let's assume a planar failure mechanism. That's a mechanism, and I'm assuming that. And I can look at this failure mechanism through this caprock system. I can search for multiple paths through this simulation result. I can then find where this critical one, so from this point, all of these paths, this has the lowest factor of safety. And then I can go and do this for every single point all the way along here and search for that. And what I can find is that when I do that, over time, I get this variation in the factor of safety that varies as I evolve a SAGD project. So if I go over time, if you look at this, the purple line is 10 years. If I look at the blue line, that's 360. You can see the variations that occurred based on where the steam chambers are, all time dependent, all dependent on heterogeneity. What's the best way to do that? Here's one of the things that we'll see presentations on in a bit is this objective function that people strive for optimization. And one of the things here is that what if your optimization, your objective function was the factor of safety? So if you look at the factor of safety, if you look at this plot, minimum factor of safety, time, number of realizations, and you can see that over a number of realizations, you get a variation at the end of the project, at the end of a time sequence, you get a variation in how that factor of safety will change with time. This is also something that you have to take into account. I'm going to make an observation that I think that one of the things we should do is rather than these sort of characteristic definitions of factors of safety, I think many of us in the simulation world now that are doing this and are worried about caprock integrity should start looking at something called strength reduction factors. It's a method that allows us to examine how our continuum, our simulation models are going to behave by sequentially reducing the strength until the system becomes unstable numerically. And what we found is, especially in the world of geotechnical engineering, is that if you build a model and then you slowly run this model and by reducing the strength with the strength reduction factor, you'll get to a point when the system becomes unstable. It predicts a particular failure mechanism, whatever it might be given your geological model, the geocellular model you put in, the strength uncertainties. And then basically what happens is that strength reduction factor becomes your factor of safety. And so there are ways to do it: plastic zones, large deformation, non-convergence in the solution, and it has a lot of power, I think, in the way we approach these things. So lots of benefits. You can accommodate multiple stress-strain relationships. You don't need an a priori assumption about a mechanism. If you've built your model to your best available information, you can run simulations, scenarios of that will actually then automatically will try and identify, given your process, what those critical failure mechanisms are. You can input appropriate constitutive behavior, especially when we use deformations a lot as a way to monitor what we're looking at. INSAR, we tilt meters, ground, surface heave, and so on. And so I think a strength reduction factor would be a very powerful way to go, since there's so much simulation work that's being done in this area. One of the things I think, if factor of safety still is something that we need to do, I think it's really important that we understand what failure means, or unsatisfactory performance means. I think there's this rapid rise in CCUS, which is a lot. I think our simulations for CCUS have to be, and I'll get in trouble for this, but I think they need to be less science and more engineering. I think at the moment, people are going to expect from us on the subsurface side very, very difficult decisions when somebody is trying to defend $1.5 billion investment in capture. Same for other subsurface energy options. How to model failure? What does failure look like? Especially if we're going to utilize factors of safety, is really important. And I think that the family of energy simulation chairs are all working in some substantially important areas, especially sort of embedding uncertainty as well, in such a way that I think we've got a good chance of capturing what those failure mechanisms look like over a range of scenarios. So with that, an acknowledgement to the sponsors, NWMO, Suncor, Cenovus, PetroChina, RIPED, CMG, and ConocoPhillips, and Energy Simulation and NSERC, of course, were the key front-end members in terms of supporting the chair, and a number of people at the bottom that have been very gracious in the provision of software that we've been using. Some of the work we're doing on in situ stress measurements with people like Nagra, and even to something like Hope Walls, who's our admin assistant, who graciously provides services for us for photography work and pictures of the group and stuff like that. So with that, a last shout out to the Reservoir Geomechanics Research Group. It's a large body of individuals who really are at the core of a lot of work that was done that supported all of this work. And so a big thank you to them, because without that, none of this would have been possible. So thank you very much.
Thank you, Dr. Chalaturnyk. Very interesting subject matter to talk about, especially when both oil and gas companies and other companies are looking at ESG issues, satisfying the investment community and the society. So quite a few good questions. First one from Dr. Iraj Ershagi from University of Southern California. He said, I enjoyed your summary of discussion. Besides all factors, it is really the large pressure gradient that must be prevented. True?
Well, this is the, this is the point about, there will always be discussions and there will always be arguments about how the models are set up, all the boundary conditions, all of the uncertainty in the geology, uncertainty in the properties. And so this was really that discussion around, if I'm trying to look at failure mechanisms and utilize the simulations, modeling has to be a part of it. Well, modeling, you're going to have to include, you include pressure transients in the modeling. I mean, it will be a part of how stress is going to evolve, deformations are going to evolve, are all going to be a part of that. So yeah, absolutely. And especially for CO2 injection and others, the large pressure transients are going to be really critical for things like induced seismicity and others. Yeah, absolutely.
Right, okay. Question from Dr. Russell Johns from Penn State University. Thanks, Rick, for an excellent talk, as usual. Caprock integrity is one of the important issues to store CO2, but another important issue for storage in an aquifer is likely regional groundwater flow. Regional flow could take CO2 away, either as a separate phase or dissolved in water to a distant outcrop. How might this leak-off influence the safety factors, and are you considering this?
So it's a perfect thing, Russ. I mean, the issue around things like storing CO2 is that what's key in all of that is a risk assessment. And so when you do a risk assessment, you're going to actually itemize and categorize a bunch of the risks that you're going to look at. And so this pressure plume, or the movement of the CO2 plume and stuff moving away from your CO2 injection region, is going to be one of the risks. And so the question would be, do we just do regular simulation work and look at it and parameterize it that way? Or should we be asking as a regulatory community, I guess, if you want, what is the factor of safety against reaching an outcrop? And then categorizing it that way, or what's the, that word that I used before, the probability of unsatisfactory performance. So if unsatisfactory performance is an excess flow rate at an outcrop of X numbers of cubic meters per day, what is the probability of actually exceeding that unsatisfactory performance? So yeah, I would suspect we are going to see a greater movement towards that kind of stuff, probabilities of unsatisfactory performance as opposed to factors of safety. Factors of safety are tough. And I drew the attention to SAGD because the language in Directive 86 asks you for a factor of safety, but really doesn't actually define the mechanism. And you need a mechanism to tie to a factor of safety. That failure mechanism is key. And that's the bit of the shadier part, I guess, the grayer part of this discussion, yeah.
Okay. Question from Maddie Kajay. It is absolutely true that FOS is related to system and not to the block-to-block analysis, as you showed in slide 14-15. The question is how to move from block-to-block factor of safety to system factor of safety. What is the worst credible approach which you can consider for risk analysis process?
So I think a lot of this discussion has been informed by SAGD in thermal discussions, right? We've been spending the last 7, 8 years looking a lot at caprock integrity for SAGD, and so that is actually why I think the language needs to change away from the factor of safety to this sort of probability of unsatisfactory performance and this strength reduction factor. We build lots of geocellular models. The kind of stuff that happens in the geological modeling, geomodeling world for SAGD is outstanding. It's incredible, the stuff that happens. If you believe in that model, we have, we use stars, of course. I mean, I'm hoping most people end up using stars. I mean, it is the model to go to. And so you have a model, you have a geomodel, which you've characterized with incredible studies. You've got a simulation tool. Well, you can do all of that, and by using the strength reduction factor, you can actually push the model to failure. It'll push you towards a probability of unsatisfactory performance. You have to do multiple realizations. It doesn't have to be a lot. But I think that's the way we've got to move, rather than saying that we have a factor of safety of 1.25. I think there's just too much grayness loaded inside of the word of a factor of safety against shear failure of 1.3 that we don't know what it means. So we might as well just use the tools we have. We now have the geomodel, we have the substantial simulation tools. Let's just move to that as a way of defining what this probability of unsatisfactory performance will be.
Yes, I agree with what you said, in that, for example, people talk about operating pressure being 80% of what you calculated. What does that 80% mean? Does it really mean that the rock may be weakened or whatever to an extent that, the room for that to be weakened? I think going back to the fundamental physics is more important. What I found from that more Coulomb failure envelope that you put in, if someone say 0.8, so divided by 1.25, that seems to cut the more Coulomb, shrink it down quite a bit. So the range of differential stress that you're allowed would be quite restricted. So I would imagine if you truly do the experimentation, like you say, over and over and over and over again, the range of friction angle may drop from 30 to, say, 28, which may mean a different factor of safety, as if it's an arbitrary number imposed after all this calculation is done. So it's quite interesting, and it really applies to different themes in terms of CO2, hydrogen, geothermal, and
absolutely.
Absolutely. Really fine piece of work.
But I think this is the final point, and I better stop talking, is that was the point about that search, is that if you look now, for all of the projects now that people are firing up wanting to do in the subsurface, quite frankly, I think many people are taking the subsurface for granted. There's a lot of surface-related billion-dollar investment people who just think that the subsurface is going to be there just to solve their problems. I think we've got to convert our conversation now in those calculations to being really trying to understand what those failure mechanisms actually look like in defining those probabilities, because we're going to have to make real decisions in the subsurface for 300 megaton storage applications, 400, 500 megaton storage hub applications. So we're going to have to push ourselves, and lots of talent in the energy simulation family to be going that way, and I expect many of our colleagues are. So yeah.
Okay. One final question is from Brian Stock. How do you propose we frame or define pushing the model to failure or having unsatisfactory results? This could be a challenge even when using a strength reduction factor.
Well, I guess this is my point, Brian, is that we all use models. Everybody fires up a model. Even if you look at the kind of work that's done in the SAGD world, I mean, we're not any different. You basically will pick a model for the caprock, and you will give it a friction angle, you'll give it a cohesion. If you're going to do reservoir geomechanical simulations to assess caprock integrity, there should be no reason. If you have enough confidence in that model, there should be no reason you can't push it to the limit using a strength reduction factor. You've given a strength value on the whole. You've looked at all of your data, all of your lab data, log data, whatever it is, and you've given it some properties. There should be, if you have confidence in the model, then you should be able to utilize that technique to push it to failure using a strength reduction technique. Nothing else changes. You're just reducing the strengths until the system fails. You can examine what the failure mechanism looks like, and define the factor of safety that way. We've got to start. We've got to start doing that, actually, so we better understand what those failure mechanisms look like. Okay.
Again, thank you very much for the technical work. Just one last comment or question I've got is, I think in addition to talking to industry members and operators, is we should be talking to the regulators as well to ensure that they understand and help them out. Okay.
Yep.
Okay. Okay. All right. So time's up. We'll go on to a 15-minute break. And thanks again, Dr. Chalaturnyk.
You're welcome.